All right, folks, let's start. Hello, everyone. This is Dr. Yuzo. This is ECE 360, Automatic Control Systems. And today is our 13th lecture. And can you guys hear me? All right, thank you, Noah. Okay, thank you, Molly. Thank you, Alex. So also being able to see my shared screen, right? So this is the Ender Dog Cam, and we are trying to, first of all, today have a summary about the steady state era for different inputs, okay? As promised by the end of the last lecture. So first of all, you got to remember, okay, what we have learned so far is unity feedback system. Unity feedback system, which means you have a system like this, whatever the forward transfer function is, the feedback is unity feedback, like this. And this is so-called unity feedback system. Okay. So this is a very important thing. In the exam, you need to take a look. The given system is a unity feedback system or not. Because even it's not, we have different way to do it. Okay, we will see later. Okay, now we just study the unity feedback system. And the derived steady state error in time domain, as you know, is equals to limitation when s approaching to 0 of a s domain division. S domain division. So in the numerator, we have s itself times r. Who is r? Who is r? Who is it? Anyone knows? No one remember? R.
Input.
Input. Good, good. Kevin is right. Okay, this is our input signal. Okay, this is input signal. And generally speaking, this is given, okay, because your steady state error is dependent of the input. So your input must be specified at first place. Okay. So the input is in the numerator times s. Denominator is 1 plus g. Who is g then? Who is g? This guy g. Who is it? Transfer function. Well, of course, transfer function, but which transfer function? This is the most critical point. What transfer function? We learned at least 4 types, right? The forward, here we go. Here we go. Forward transfer function. Forward transfer function. Very important. Very important. Forward transfer function. Not any other transfer function. Okay. Forward transfer function. And we also need to be careful. The forward transfer function need to be either given or organized to be in this format, in where you're seeing bench of zeros and bench of wholes, and also what? S term in the denominator, S term in the denominator, and the order of this S term in denominator n, letter n. Let me use another different color, which is black. N is called most important, one of the most important concepts we learned. What is it? System type, system type. Here we go. Obviously, Noah has reviewed the last lecture. Very good, very good. It's called system type. Okay. Be very careful. We're talking about forward transfer function, and from where we get the system type. Of course, what if n less than 0? It's of course n is possibly less than 0. What happened? It's just like this, right? If, for example, you have s plus 1 here, you have s less than 0. Let's say you need 2. How about that? And then s plus 2. In this case, be careful. It means essentially what? Essentially means this. Does it make sense? This is how you understand the n less than 0. This is how you understand that. Okay. But generally speaking, we won't see negative n in the denominator. Instead, what we are seeing is s term in the numerator. They're equivalent. Okay. This is representing negative system type. However, we won't be able to see such scenario because what we will be able to see is this way. They're equivalent. Does it make sense? Okay. So here, this system is what? -2 system type, right? -2 system type. Mathematically, it exists, right? It exists. This is how you understand negative n. How you understand negative n. Does it make sense? Any questions so far? All right, if this is fine, then we can move on. Just based on these, we are summarizing the three different types of inputs. Okay. We, generally speaking, just study these typical three: step, ramp, and the parabolic. Right? Step, ramp, and the parabolic. And they're generally speaking given. However, only one thing you need to be very careful on this input, which is the given might be in time domain function or the S domain like this. If the given input is in time domain, you need to do a what? Laplace transfer. You probably gonna do this if you see in examples. Okay. So for now, what matter is the summary. So for three different input, we respectively have such kind of a conclusion. Okay. So first of all, for the step input, if you substitute this input, which is R, obviously this is R, right? This is nothing but R. You substitute this R back to here, and then find a limitation. And then you got the steady state error. No problem at all. However, here the summary here is trying to give you kind of conclusion, make your calculation much easier. So when n is less than 0, or n equals to 0, or n is equal or greater than 1. This is trying to cover all of the possible integer value of n. Because n obviously is an integer, So when n is negative, which means there's no s term in the denominator, instead have s term in the numerator, then what can happen? Steady state error is a finite constant. Okay, finite constant. What's the specific value? Well, of course, it's up to your calculation then. Right? And when n is equal to 0, steady state error going to be a finite constant as well. And when n is equal or greater than 0, the steady state error is 0. Okay, this is the conclusion. And here, pretty much again, cover all of the possible integer n value. Okay, and correspondingly, your steady state error could be finite constant or 0, depending on the n value. So from here, you can easily tell, given the step input, then you observe the system type. If you see the system type is 2, what's your conclusion on the steady state error? Once again, the given input is step, then you observe the system type is 2. And what is the steady state error? Zero, directly 0. Does it make sense? Because as it says, system type 2, n is equal to 2. And then steady state error is 0. Okay. And what does it mean? It means you don't need to go through this calculation. Save these, right? This type is 2. Okay, directly you steady state error is 0. Done. Okay. Of course, if the system type is 0, what do you need to do? Well, you need to solve this. You need to really go through this. You need to go through this. You have to. Right? And you're expecting to see a finite constant as the result. Does it make sense? Everything? This is what this summary for. Okay. Does it make sense? Any questions? No questions? Then I have one for you then. The steady state error. What is the best steady state error? What's the optimal steady state error value? In other words, is a value the bigger the better, or the smaller the better? But don't forget, this is about how we are evaluating the system, right? From the output, we are evaluating the performance of the system. So what we say? The smaller the better, or the bigger the better?
Don't we want smaller?
Absolutely smaller. Okay, absolutely smaller. Okay? The smaller the better. That's because it's called an error, right? From the name is very meaningful as well. Smaller the better. That's the error. You don't want. So what is the optimal value? Of course, 0 is the greatest result we could have. It's 0. There's no, which means what? No error, no steady state error. No steady state error means what? Perfect. Your output at least a steady state. Okay, the transit we don't know yet. Okay, this module is not studying the transit. We are not evaluating the transit. We just talk about a steady state value. At a steady state value, guess what? No steady state error. Great. Okay, great. That's what we want.
Of the system, like the larger that is, that's technically reducing what we'll see on the end of the output, right? That's why, right? We want a lower error.
Yeah, sure. A steady state, I mean, your reference like a 10, your eventually steady state end up with what? 7. The steady state error is what? 3.
Okay.
Of course, the smaller, the smaller the better. The smaller the better. That's exactly the visualize the meaning of the steady state error. Okay, so keep this in your mind.
Not to go too much in depth, but is this similar to like when they have an output buffer for like BJT or something like that, where they want something that has some feedback to it to reduce or to be able to capable of like a load? Is that kind of why they have feedback, or no?
As far as I know, your output buffer is trying to take care of the output impedance rather than provide any feedback.
Okay.
Yeah. Electronic circuit, basically, John is asking. So what do we do to the output? Because you're feeding load, right? How to make your load to receive the as high as output voltage as possible? You need the output buffer. But similarly, in the input, you might need an input buffer as well, okay, for the same reason. Anyways, coming back to here, this is steady state error. So what a conclusion we can have here is this, okay? So we need system type, okay? System type 1 and 1 plus to make what? Steady state error 0. So you're observing the system type. You got, well, okay, this is system type is 2. Guess what? To step input, there's no steady error for sure. Okay, very happy to see that. Very happy to see that. And the system type 1 and 1 plus also means what? According to the definition here. 1 or 1 and 1 plus what? 0 poles. Does it make sense? If n here is equals to 1, that's what system type 1, and you have 1 0 pole. So n here is also the number of the 0 pole of this forward transfer function. Does it make sense? Is that kind of description making sense? All right, if so, then we can move on. Next, for ramp input. Well, what does it mean by ramp? In frequency S domain, what you see as numerator here is S squared. Okay, this is a ramp input, and the numerator, I mean the denominator, you're seeing S squared. In the numerator, it might be any constant, a different constant value, just a coefficient or gain. It doesn't matter. So to the ramp input, if n is equal or less than 0, steady state error gonna become what? Parable. We just mentioned the smaller the better, and now we are seeing what? Steady state error might be infinity. This is absolutely terrible. And if n is equal to 1, which means system type 1 steady state error is finite constant. And now you see why we are adding a finite, okay, here, before the constant. It's trying to differentiate from the infinity, right? Infinity is infinite, right? And the third category is if the system type is 2 or higher, steady state error gonna be what? Anyone can guess? System type 2 or higher, steady state error gonna become what? Any guessing? Here we go. Alex is right. 0. 0. So we circle this and give a check and saying we need system type to be 2. Or I think I should use or, not and. Or 2 plus to make system steady state error to be 0 for ramp input. Okay, never forget the steady state error is input dependent. You need to specify the input and then talk about the steady state error. Without specifying the input, you can't, generally speaking. The type 2 system has what? A steady state error of constant or 0 or infinity. No, you need to specify the input first. Okay. And also, it means your forward transfer function needs what? 2 or 2 plus 0 poles. Right. This is the for ramp input for different type of system. You have different steady state error. Third one is parabolic input. You have n equal or less than 1, equals to 2, and equal or greater than 3. And steady state error, respectively. Anyone have any guessing? If the system type is 1 or even less to parabolic input, what is your steady state error? Can you see the pattern roughly? What's the pattern roughly? The higher system type, the what? Lower possible steady state error, right? Of course, we are not specifying the input. That's why I'm saying possible. Right? But to exactly same input, we can safely say the higher the system type, the smaller the steady state error. Does it make sense? So what could be the possible steady state error? Only 3, right? Only 3 possible values. What are they? Infinity, finite constant, and 0, right? With the increase of the system type, your steady state error is decreasing. And here, the system type 3 or 3 plus to make 0 steady state error, which also means you need 3 or 3 plus 0 poles in the forward transfer function. This is a summary. What do you need?
So for a step
yeah,
input,
go ahead.
None of them can be infinite. They're always a finite, or 0.
Exactly. So step input cannot give you a infinity as the steady state. You won't see an infinity steady state error. You won't see it.
Okay.
Yeah. Step input. Well, this also explains why we always use step as a input to test your system, right? Because it's safe. You use a ramp or a parabolic, guess what? Your result, your output might end up with infinity of steady state error. Well, this is very dangerous for testing a system. We don't dare to do that. Okay. Step input is safe. That makes sense. Step input is safe.
But when we're saying in terms of ramp, we're saying that whatever signal we're ramping would be theoretically continuing to infinity itself, right?
Yes.
That's basically why, because like why the step will never be infinite is because there's a limit, which is whatever our input is, right? Whereas ramp and parabolic, we're saying our input is going to theoretically also itself go to infinity, right?
One is basically right, but you need to be very careful to differentiate the steady state value and steady state error. Let me give you an example here. Say your input is like this, right? It's a ramp. Your output is like this. So what is the steady state output? Steady state output, steady state value. What is it? What is it? Anyone knows?
We wouldn't subtract the input from the output.
Is it? No. I'm asking, what is the steady state value?
I don't know.
Well, your output is a ramp. So what is steady state error? Oh, I'm sorry, steady state value. Anyone knows? Anyone knows? What is steady state value? No one knows?
Well, it should follow some sort of a ramp fashion because that's what our input is, right?
No, your input is down here. You're trying to say you were basically right. Okay, your input is approaching to infinity, is very likely to lead your output to infinity as well, right? I'm now giving you an example to prove what you just said. So what is the steady state value of this output? What is it?
Isn't it just a function?
No. So even the function, you need to have a concept of steady state value. What is it? Here, of course, this is the x-axis is t. The y-axis is c of t, or say the signal of t. So we can plot either input or the output here. So what is the output here? Steady state value. Here we go. Clay is right. Your steady state value is nothing but the infinity. Does it make sense? Very good. The Clay is right. Okay. Does it make sense? Steady state value is infinity. Does it make sense? It's approaching to infinity. What does it mean by steady state value? When you try to express the steady state value, what is it? Lowercase c, lowercase c of what? T equals to infinity. And when we talk about steady state error, what is it? Lowercase e when t equals to infinity. These two are different. Does it make sense? So go back to here. C of infinity equals to what? It's a ramp. No matter how you make this happen, it's a ramp. C of infinity equals to infinity. Does it make sense? This is the concept of steady state error. Okay.
And so the error is essentially just taking C.
No. Well, wait a minute. Let's clarify this before going to the steady state error. So in terms of steady state value, does it make sense? Everybody.
I understand the steady state value part. Yeah.
How about others? No? Any questions? Then how to? All right, Winston is fine. All right. Any questions then? If no question, we move on to the next steady state error. Okay. Steady state error is what? This system. Steady state error. What is it? Here. System. What is it? What is steady state error?
Isn't that the output subtract the input?
At where?
Well, whatever the steady state instant in time is.
Yes, at t equals to infinity. Therefore, the steady state error is what? The concept is correct. So what is the result?
Oh, C of infinity minus R of infinity.
Therefore, equals to what?
E of infinity.
Infinity as well.
So if we find that our output isn't of the same slope as our input, that is what indicates that it's infinity, correct?
Yeah.
Whereas if we find out that the slopes are the same, but it's offset, that would be the finite constant.
Correct.
And if they're exactly the same slope and exactly the same output, that would be 0.
Exactly same offset.
Sorry, yeah, offset. Yeah, okay. That makes sense.
Exactly right. Okay. Is everyone following? I think this is a very, very interesting discussion. I think is clarified as very to this such kind of input ramp, and what does the infinity of steady state error look like, and what does the finite constant steady state error output look like, and what does the zero steady state error output look like? And John just summarized them very well. Any questions? Any questions?
Yeah, real quick.
Sure.
For the ramp, does it kind of look like the sinusoid you have for 1, but instead it's centered along that line?
For the ramp, which signal you're talking about, input or output?
2, right by 2. That graph you have there.
And where is the sinusoidal, you mean?
The along that C line
Along
that
the
you have there.
C.
Would it be like going back and forth over that line?
Oh, you mean the transient? Yes. That's
Yeah.
possible. The transient possible. It possibly like this.
Okay. All right. That's
Absolutely. Yes. Yes. Of course, here I'm skipping the transient. The transient absolutely possible. The input won't have any oscillation here. Input is directly the ramp. However, output has oscillation as the transient, and then after a while, you just convert to this ramp straight line. Yeah, there is a transient. Yes, you're right. You're right. Okay, you're right. Any other questions? All right, if this is fine, well, keep this notes, okay, because the following examples require these this summary, making your calculation much easier. I mean, here system type 1, you directly give a 0. You don't need to do any calculation, right? To this two case, what do you need to do? You need to really substitute R by the step, and then really find this limitation, right? And to here, obviously, this case and this case, you directly can have the result without going through any calculation. But the second case in the middle here, obviously, you need to really substitute ramp into R here to do the calculation, to find that so-called finite constant, right? So this is what this summary for, okay? Saving a lot of time. So let's just apply them onto some examples. Unity feedback system has forward transfer function as this. The questions are very simple. Just to find the first system type, second steady state error for different inputs. Inputs of 80 u of t, 80 t u of t, and 80 t square u of t. This is the first example, so easiest case. Right, so let's solve this problem together. Solve this problem together as the first example. Question 1 is asking for the system type. What you need to be careful is see if this the forward transfer function, and we see the problem is so nice that g of s is nothing but the forward transfer function, from where you can tell the s-term order in the denominator. You find order of s is what? What is the n value here? 0, right? So this is what? System type 0. Yeah, system type 0. System type 0. The second, start to find a steady state error. Steady state error. But be very careful. We are seeing 3 inputs, and all of them are given in what? Time domain. Okay, so they're not S domain yet. We need to convert them to S domain. S domain. How to do that? We need the table, right? We need the table. We need a table. We need a table, the handout table. I mean, so here we go. Okay. This is the table we need to apply. So first one, the 80 times U of t is a step response, unit step response. So 80 constant A basically. 80 times U of t correspond to S domain what? 80 over S. Right? Just like this. You're applying the Laplace transform. Then we have 80 t squared U of t. And then you find the S domain expression, right? Based on this table. And after doing that, you can tell this is what step. This is a ramp. I'm not surprised. This is parabolic. 3 different input. And then we start to draw a conclusion. Three result. And then we go back to the summary table here. What do we see here? This is to first step input system type 0, right? Remember? What is the steady state error? System 0 and the steady state error finite constant. Finite constant means what? Means you need to really do the calculation. Substitute R here by the step, right? So go back to here, limitation S approaching to 0, and numerator as S times the input, which is 80 over S, and then 1 plus the G, which is this. Right? Does it make sense? If this is clear, then we don't need to rush to find out the value. We just need to look more. The second input and third input, ramp and parabolic, what do you see by reading? System type 0 for ramp means what? Infinity of the error. And for the parabolic input, the system type 0 means infinity of steady state error as well, right? So come back here. These two, no matter what, they're definitely infinity. We don't need to bother using the equation, the formula. I'll give you guys 1 minute to find what is the limitation value of here. 1 minute. Go ahead. No. Yeah. Hold on. Oh yeah. Yeah, Kevin is right. It's about 0.625, right? Yeah, so how to do this? So first of all, in the new here, these two s canceled, right? There's two s canceled. And then what do you got? The rest of the thing is, what you need to do is just substitute s by the numerator is 80. Denominator is 1 plus, and then here's square times 8, and then here is 7 times 9, right? This is the value. This is how to find the limitation value. It's not very difficult. By the way, have you guys learned how to find the limitation value from math class? Which math class teaching limitation?
For me, I think it was Calc 2. You're referring to like L'Hopital's and all that.
Yes.
Theory of summation or series and stuff like that in convergence. Okay.
Calc 2, yeah, Calc 2. That makes sense. Good. It should be before the differential equation. Actually, it should be before the differential equation. Good. And here, of course, we're missing a couple of things. First, here, I give you another 2 minutes to find out these two inputs in S domain. Find out these two. Another 1 minute. Go ahead. Or let's see, what is the S domain function for this ramp? What is it? 80 over S, right? Square, of course, S square. Okay. How about the third one? The third one is 80 over S cubed, right? Any questions? You really should. Okay, you really should have questions. As Alex mentioned, be very careful. Okay. So you prefer to make such kind of mistakes now, okay, rather than the exam. Okay, because this is something happened very often. This is the correct result for this Laplace.
So these limits, they're only applying for unity negative feedback, right?
Yes.
So positive
Why is that?
feedback,
Why is that? Why is that? Why is that has to be negative feedback? Do you know why?
Well, I mean, we derive the formulas originally.
Exactly. That's exactly. Okay. We derive this formula based on negative. Remember, R minus what? R minus G, R minus C, right? Rather than R plus C. Good.
So because negative feedback, the error signal would be a reduction of the steady state value. Positive would be an addition. Positive feedback would be an addition.
In the equation, derivation equation, yes.
Okay.
And here, well, Sean is asking, not quite relevant to this step, to this parabolic input. But everybody be careful here, okay? The parabolic here is half a times t squared is equals to a over s cubed. Okay, be very careful. That's why it's 160 as the numerator here. Okay, be very careful. Very easy to make mistake here. It doesn't matter to this result as it is infinity as the result. However, when it does, okay, in this 80 and this 160 is half. It's 50% different. Any questions? It's not difficult, right? Oh, by the way, what we should do today? Anyone knows what we should do? Anyone knows where? What we should do? Review. Here we go. Yeah, very good. Emily is right. Yeah, today is review for midterm 2. Midterm 2. I'm sorry I'm giving some bad news in the middle of the class, but hopefully it's not frustrating you. On the contrary, reminding you for more attention. All right, let's take a look at the example 2. Example 2, okay, a system block diagram given as this. Then find first the system type. Instead, it's error for inputs of 5 u of t, 5 t u of t, 5 t squared u of t. I think it's give you guys 8 or 9 minutes or so, up to like 2 p.m. Do this yourself all over. All right, go ahead. All right, I think 9 or 8 minutes are too long, I think, for such kind of problem. So we can take a look at the solutions now. First, system type is fairly easy, right? But even this time is block diagram, and you need to understand from a block diagram who is, or how you can find the forward transfer function, right? So forward transfer function in this particular example is just this guy, right? Right, just this guy. Very nice, just here. Right? Therefore, the system type is 1, right? Order of s in the denominator is 1. Type 1 system. Type 1 system, and then second, start to study what is the, you can easily define the inputs as R1, R2, and R3, right? Respectively. So they are 5 over S, 5 over S squared, and what? 10 over S cubed, right? And we know that they are step, ramp, and parabolic, respectively. And once again, we need our summary where we can find to type 1 system. What do you see? Anyone? This guy equals what? 0. Good. This guy equals what?
455.
Is something finite constant. 2 is basically at least the right track. We don't need to worry about the specific number yet, but at least you know this finite constant, which means you need to substitute the R by this given input to find the limitation. And this guy equals what? Infinity. You got 2 out of 3 at least immediately, right? The next, just S is there first times 5 over S squared, and then 1 plus the G. So the G is 10 times square times another square, S times square parentheses, and times another parentheses. That's what I mean. And what this result is. So first, this S is canceled with this S here. And then what you got? What you got is numerator is 5. But this S needs to be times into the denominator. Okay. Therefore, you end up with 10 parentheses, parentheses, and the parentheses and the parentheses in the denominator. Because this S here gonna be canceled by this S. Okay. Once again, this S gonna be canceled by this S. Does it make sense? And then you substitute S by 0. You end up with a constant, which is 25. It's actually exactly 25. Yep, Kevin is right. It's half. Done. This problem is done. The problem is done.
The error transfer function, that's the numerator is S multiplied by R, right?
Correct.
Okay.
Yep. Don't mess up with that. Okay, it's S times R, and whatever R is, you substitute into it. Any other questions? All right. Hopefully, no questions in the exam as well. Now let's talk about the midterm. Midterm. EC 360 midterm 2. Let's see what we're gonna have. First thing first, exam time. What is it? When is it? Anyone knows? First time Wednesday, 1 p.m. Sounds great. Sounds great. Sounds great. Which is what, October 21st, right? Is Wednesday, which is October 21st. 1 p.m. to 2:30 p.m. Of course, once again, You have 15 minutes to post. This is the lecture time. Yes, lecture time. Correct. Okay. Second is, what do we have? No multiple choice this time. And are you guys smiling? Oh, cannot see any, but I believe so. And we have 5 problems to calculate or analyze. Yeah, thank you, Noah. Let me see your smiling face. Appreciate that. I think one of the biggest issues online teaching and learning is I'm not able to present or exhibit my sense of humor. It's very, very tough to do that. But hopefully the pandemic is over as soon as possible. Now, problem 1 is first order system, and to find the settling time and resting time and the TC. What is TC? Anyone still remember?
Time constant.
Time constant, very good. And thank you, Lucas, for the compliment. The only thing that you guys want to be careful, okay? I might ask one of them, any one of them. I might ask any 2 of them, or maybe I ask all of them. So you don't want to present anything I'm not asking for. Okay, so always remember this. Okay? Read problem carefully. I'm not necessarily asking for all of them. Okay? Not necessarily. Of course, the given is transfer function. I have to give you the transfer function. I have to give you the transfer function. This first order system transfer function. And also the specified input. Remember? Your output is time response, so-called time response, is input dependent. So is the steady state error. Okay, always remember these 2 modules about output, steady state value, output transient or output steady state error. They're all input dependent. Without a specified input, you won't be able to find any. Okay? There's no uniform answer. There's no uniform answer covering all of the possible inputs. It doesn't exist. This is problem 1. We have example. Okay, all of these problems gonna have corresponding examples in the lecture to review. Okay. Problem 2 is what? Second order system. Given either transfer function or block diagram. And find what? TS, TR, TP, and overshoot. And the this time is once again a second order system. A second order system. Just reminding you that we have what? We have a formula. Okay, formula in terms of what? Zeta and omega n. Remember? Who is zeta? Anyone remember who is zeta? Damping ratio. Omega n is what?
Natural frequency.
Natural frequency. Here we go. Okay, so those formula are in terms of those two guys. If you're free to use, if you're free.
And the natural frequency, can't we use the natural frequency and then convert that to frequency in hertz and then find the period? So like if we were given a visual waveform, can't we use omega n from, one cycle to another to figure that out as well, or no?
First, if there's no damping, then that is completely correct. Does it make sense? If no damping, or say damping ratio is 0, that is completely correct. But if there's damping, your oscillation frequency is the same as the no damping.
I mean, like the underdamped system case. I mean, if as long as it wasn't critically or overdamped, couldn't you still find the time between those two to find omega n?
It should be okay, but I never tried that before. It's a good question. It should be. It should be okay, because that's the definition of the natural frequency.
Because like if we have the distance.
I understand what you mean. The distance or say time moment difference between two zero crossing, well, not zero crossing, the steady state error, steady state value crossing moment, right? Oscillation.
Yeah.
I know what you're saying, but I never do that. I'm not. Should be okay. It should be okay. I'm not just quite feel safe since I never tried that. You can use MATLAB to try some and then to see if you can end up with a reasonable value. You got 2 time moments and then you find the f, right? And you time onto 2 pi, and then you see if it's equals to omega n, right?
Yeah, it'd be 1 divided by 2 pi.
I'm always surprised if they're close. It should be. It makes sense. From the definition wise, it makes perfect sense. And also here, this problem too, obviously, you not only need the formula for these 4 specifications, but also you need what? The table, remember. The table is for what? Anyone answer? The table, the handout table is for what in this problem too?
Rising time.
Rise time.
Very good, very good, very good, very good. Yep, obviously 2 is on the right track. He understands what I'm talking about. Okay. The table is used to find this table is lookup table, right? The lookup table. And rising time. This is problem 2. Need to find. Oh, there's one more thing. Who can remember what else we also look for in problem 2? Say that again.
Steady state value.
Very good. Steady state value. Great. Okay, you need to find steady state value. Okay, remember this. You need to find steady state value. Very good. Problem 3. Problem 3 is what? Oh, problem 3 is probably a little bit new, but it shouldn't be very difficult either. It's still about the second order system. Okay, second order system. But this time, the given is not transfer function, but given is the output signal graph. And then what do you need to do? This time is not find, it's the estimate. It's also find, but your estimate, basically. Your estimate. What does it mean by estimate? Estimate means read. You need to read the given graph to tell what? To tell everything above. Basically everything above. Okay, read the problem carefully to see what I'm asking for. And how to find them, read the given graph. You understand the definition, you understand the calculation formula, and then do you understand them when you see them? You recognize them when you see them. Okay, that's the problem 3 is for. Okay. So you're talking about second order system. It's given the graph, output signal graph. And this problem has a 5 points extra credit for something, which I won't tell for now. Okay. Extra credit, okay, 5 points. If you have an extra credit point question, extra credits question, 5 points. This is problem 3. Problem 4. Problem 4 is basically about today's lecture. It just what I mean is unity feedback system. And find what? System type. Second, steady error for inputs of, right? Yes. Problem 4 is about today's lecture. And problem 4 is today's lecture. And here, the given, as you can see from different examples, either transfer function directly or block diagram. Or block diagram. Not difficult, that's good. Then make sure you are spend as less time as possible, and also 15 out of 15, right? You want to reach 15 out of 15. Losing points on something you know very well is bad. This is problem 4. And the problem 5 is problem 5. Problem 5 is what? And problem 5 is next lecture. Does it make sense? Is non-unity feedback system. It's not surprised. Find what? Find everything above. Find everything we found from previous problem 4. This is the next lecture, problem 5. You need to attend the next lecture to know what we're gonna have. Does the homework 3 have an example of non-unity feedback? But to be very honest, I can't remember. I really can't. Homework 3 problem is. But next lecture we'll definitely do. Sure, absolutely.
So
I mean, you won't, in my exams, okay, you won't have a scenario in where the exam problem or something, you never had a corresponding example studied in the lecture. That's impossible. Okay, if anyone can present a case like that, let me know. Okay, I will give you some extra credits because I'm pretty sure it never happened before. Are you going to give a case?
Yeah, for the, since we're only covered the negative unity feedback system, are we going to be doing the positive unity feedback system, or?
You're really trying to give a case? No, that's not possible. No.
For number 4 on the homework.
Number 4 of the homework. Go ahead.
It shows a circuit with a 5-volt supply, a switch that closes at T = 0, a resistor and a capacitor in series.
Mm-hmm.
What was my question? Oh, would the transfer function, it's asking for the voltage over the capacitor. So would the transfer function be in terms of the voltage over the capacitor?
The transfer function over the, yeah, you need to find the, because you have a switch, right? The switch represent a step input. That's the input. And then the output is the voltage across the capacitor, you said. So
Yeah.
the output over input is the transfer function you're looking for.
So I switch it all into the phasor domain, and then I got my
phasor domain. No, don't say it's phasor domain. It's frequency domain.
Frequency, right? So I got my function for V of CS.
V of
V, or the capacitor over the voltage. I got that function.
Well, you need a transfer function. Transfer function is that voltage, output voltage divided by the input. So you are basically assuming step input, and then so when you derive the transfer function, you have 2 unknowns. You're considering your output and input both as unknown, as 2 unknowns. And then you derive that transfer function. Rather than deriving the output voltage expression, that's not transfer function anymore. That's the output signal expression.
Okay, so my transfer function is
Yep. Meaning the output over input, that's the 2 unknowns. You're deriving this ratio between these 2 variables.
Okay. All right, that makes it a little more clear. Thank you.
Sure, absolutely. And then based on that transfer function, okay. And then now you close the switch, which is representing a step input. Okay, you know the input as well. And then you have the input specified input. You have the transfer function, and then you have both. You can find the steady state error. Okay, that's how we go from there. So basically, this particular homework problem has more than our in-class examples, more complicated because the transfer function is not directly given. However, in our upcoming exam, the transfer functions or block diagram containing the transfer functions will be given. Okay, will be given. So don't worry about that perspective in the exam. However, yep, I just explained how to solve that homework problem. All right, folks. I think that's all for today. And if any questions, you can go to the Teams. Find me. It's my office hour from now on up to 4 o'clock. Okay. Thank you for attending today's lecture, and talk to you guys next Monday. Thank you. Bye.